So in the first part of this experiment, you're going to be making a pinhole camera. So aluminum foil works best for this, but if you don't have a piece, you can use scrap paper. The foil will block more of the light. So we're going to use our pinhole camera to study the sun. So to make your camera, all you need to do is to take a needle or a thumbtack or a really fine mechanical pencil and just poke a very small round hole into your foil. If you're not happy with your first attempt, you can tape this over and just try again. The next thing that you're going to do is you're going to take your piece of foil and you're going to tape it to a window that the sun comes through. Now, if you don't have a window like that in the house where you live, then what you may need to do is you'll need to take your piece of foil and two long pencils or something and rig up a little screen that you can stab in the ground and then do the experiment outside. But it is easier if you can find a window that you can tape the foil to. Now, you won't be able to see this in the video, but there is a very tiny little image of the sun on my page now. So the light leaks through here and forms an image on the page. And we're going to take some measurements off of this. So the first thing that we want to measure with our pinhole camera is we want to figure out how big the sun is. So what the diameter of the real sun is in kilometers. And we could do this using our pinhole camera because due to the symmetry of the angles of this setup, the ratio of the size of the sun on the page to the distance between the image and the pinhole is the same as the ratio between the size of the real sun and the distance from the sun to Earth. So the ratios are the same. So what we're going to do is we're going to measure the size, the diameter of the sun on the page. So you'll write that down in your notebook. And you also want to figure out what this diagonal distance here is. Now that's hard to measure with a ruler. So what's probably easier to do is you will measure horizontally over from your image to the window. And remember, if the tick marks on your ruler don't start right at the end, then you'll need to measure this distance here and add it to your measurement. But you get the measurement from the image over to the window. And then you also want to get this vertical distance here. So from the book up to the pinhole. So you'll have this distance and this distance, and then you can use Pythagoras' theorem to figure out how long the diagonal is. And the lab manual gives you the formula for that. So you will have the diameter of the sun on the page and the distance between the image and the pinhole. And then we're going to plug in the real distance between the sun and Earth and figure out what the diameter of the sun is in kilometers. So we'll have figured out the diameter of the sun using just a pinhole camera. The second thing that we're going to measure with our pinhole camera is we're going to measure how long Earth's day is. We expect that to be pretty close to 24 hours, of course. So the way you start this one is you want to come in here and mark the location of the sun on the page as accurately as you can. So I'm just going to draw a little circle around the sun. And then you also want to write down the current time. Then you're going to wait at least half an hour, but 1 to 2 hours is better. And what's going to happen is that the image of the sun is going to move across the page. So just as the real sun seems to move across our sky, this little image will move across the page. So you'll wait at least half an hour, but preferably 1 to 2 hours, and then you'll see that the sun has moved, and you'll mark that location and also write down the time. And then what we're going to do is we're going to measure the distance that the sun appeared to move across the page. We already have this distance, d, and using those two quantities, we can figure out the angle that the image of the sun seemed to move through. And that's exactly the same as the angle that the sun appears to move across our sky. So we'll be able to use the time difference between the two readings and the angle that the image moved through to figure out how long it takes the sun to appear to go once around the Earth, which of course is the length of the Earth day. And again, we expect that to be pretty close to 24 hours, but we will compare our experimental value to the known value of 24 hours with a percent discrepancy calculation. So using just a simple pinhole camera, a hole punched in some foil, we are able to take some real measurements relating to our sun and its apparent motion across our sky. In this next part of the experiment, we're going to be looking at the sun and specifically sunspots using NASA's SOHO observatory. The lab manual gives you the web address to get to this page, and on the landing page, they always have an image of the sun that was taken today. So this is what the sun looks like today, and down in the corner, they show you how big Earth is in comparison to the sun and how big Jupiter is. So the first thing you'll do is you'll look at this and see if you can see any sunspots. Now, sunspot activity goes in an 11-year cycle, so there'll be peaks and minimums in how many sunspots you see. Unfortunately, 2020 is right in the middle of the Maunder minimum, which is when there's relatively few sunspots visible, so it's pretty likely you won't see much, but have a look anyway. So to actually study the sunspots, we're going to instead be looking at the archive of images. So right underneath the picture, there's a link that says List of all available daily images, and you click on that, and you get taken to this page where there is an enormous number of sunspot images. So they've been taking data since 2006, 1 image per day. So we're going to be scrolling down to look at the largest sunspot seen in the last 30 years. And that was in October of 2014. So you scroll down to 2014. And we want the 10th month, and you're going to be looking at data on particular days. So the lab manual tells you which days to open up, but just to give you an example of what you're going to be looking at, I'll open up 2 of them for you here. So here's the sunspot taken on October 21st, 2014. And as I said, this was the largest sunspot seen in 25 years at that point. So you'll have a look at this, and you'll also look at it on different days, because what you'll notice is that if you go to a different day, so this is 2 days later, it looks like the sunspot has moved across the surface of the sun. That's not actually what's happening, however. The sunspot's mostly staying still, but the sun is rotating. So by watching this sunspot over the course of several days, you're going to be able to calculate the period of rotation of the sun. So how long it takes the sun to rotate once. You're also going to be looking at things like whether sunspots change in number or position over the course of several days, and also whether you think the axis of rotation of the sun is parallel to Earth's axis of rotation, or whether they're at an angle to one another. So the lab manual will step you through what you need to do for this part of the experiment pretty well.